I will be presenting Summit, Source-Free Adaptation of Uni-Modal Models to Multimodal Targets, which has been accepted for poster presentation at ICCV 2023. Summit builds upon previous unsupervised cross-modal adaptation works, which leverage cross-modal correlations to improve performance over previous unimodal unsupervised domain adaptation works. While these methods work well, they assume that not only is the source dataset available during adaptation, presenting several logistical issues, they also assume that the target dataset sensing modalities match exactly with the source dataset. In the event that the target data modalities were to change, such as with the addition of a new sensor, the source models would have to be retrained from scratch, and likely a completely new source dataset would have to be collected and annotated. This is very costly and time-consuming. In Summit, we relax both these assumptions simultaneously to create a new source-free adaptation setting where unimodal models are adapted together to multimodal target datasets. Since we require only that a unimodal source model exist for each target data modality, we can easily adapt to different target data modality configurations without having to annotate a completely new dataset every time. In addition, we don't have to spend any resources maintaining large source datasets, which has grown large enough in recent years to start to present their own engineering challenges. To address this new setting, we propose two alternative pseudolabel fusion methods, agreement filtering and entropy weighting, as well as a data-driven method to automatically switch between them. The fused pseudolabels are then used to guide the adaptation of the source models. The first pseudolabel fusion method, agreement filtering, works by first calculating a unimodal pseudolabel for each modality. We remove any unimodal labels which are not sufficiently confident in their predictions, and then we check for agreement across modalities. Any pseudolabels that disagree across modalities are ignored, and we're left with a set of pseudolabels that are both very confident in their predictions and agree across modalities. The other pseudolabel fusion method, entropy weighting, works by taking a weighted sum of the output distribution of the pseudolabels. The distributions are weighted according to the entropy of the distributions, with more weight being given to the more certain distribution. By taking a weighted sum, we allow a very confident prediction to override a less confident prediction. However, this can also allow noise to be transferred between modalities, and so it shouldn't be used in cases where we expect very noisy performance, such as when the domain gap is particularly large. To switch between these two pseudolabel fusion methods, we compare the expected agreement between the source models to the actual agreement on the target data. The expected source agreement is the product of the top one accuracy of the source models, and the target agreement we calculate from the actual predictions on the target data. Since correct predictions must agree with each other, if the source and the target agreement are very similar to each other, that means that the source models are performing very similar to how they performed on the source data, and the domain gap is likely small. In this case, we would pick entropy weighting. Otherwise, we would use agreement filtering. Here, in the case of USA Singapore and the day-night experiments, which are both splits of the same dataset, we can see that the source agreement and the target agreement are very similar, so entropy weighting is used. However, in the case of A2D2 semantic kitty, which adapts across two different datasets, we can see that the ratio is much smaller, indicating a larger domain gap, and agreement filtering is used. We perform a set of 3 adaptation experiments in our setting, modeled off of previous unsupervised cross-modal adaptation experiment. The critical difference here being that the source models are trained completely independently of each other. We can see that our method consistently performs the best out of any of the source-free methods, and it even outperforms methods which assume access to paired multimodal source data. If we take the time to further examine the performance of each individual fusion method, we can see that throughout the experiments, both methods offer some improvement. However, neither method is strictly better or worse than the other. If we look at the methods that the switching method has chosen, highlighted in yellow, we can see that our switching method does consistently pick the best method for fusing pseudolabels. While our source models were trained independently of each other, they were still trained on corresponding samples, And so it is possible that some cross-modal correlations were learned implicitly. To account for this, we ran another set of experiments, the crossover experiments, where the source models, in addition to being trained independently of each other, are also trained on mutually exclusive partitions of the same dataset. The source models are then adapted to a third dataset. As we can see in our table below, this is a much more challenging setting where our baseline methods provide very little improvement. And while this setting is challenging for our method as well, we can provide a much stronger improvement of around 10% consistently across the crossover experiments. In the following short clip, we show the performance of agreement filtering on the A2D2 semantic kitty experiment. We show the output of each modality independently, as well as their combined 2D plus 3D output. Please note that even though we're showing a video, each frame is processed independently. Thank you for watching our presentation. We encourage you to visit our ICCV poster if you'll be attending in person, and to read our paper for further details.